In 2009, an active Iridium satellite and a defunct Cosmos spacecraft collided over Siberia, closing at relative speeds exceeding 10 kilometers per second. The impact instantly generated a cloud of over 2,000 pieces of trackable shrapnel, dispersing high-velocity fragments across a wide orbital plane. This visualization tracks a metric called the crash clock, which researchers use to measure the systemic stress of the entire orbital environment. In 2018, prior to commercial mega-constellations, the crash clock stood at 164 days, over 5 months of buffer time between high-risk conjunctions. By mid-2025, the massive influx of new satellites compressed that temporal buffer to just 5.5 days. Earth's orbit has transitioned from an open expanse into a congested, high-velocity corridor where object density significantly elevates the chance of contact. We are managing a system where the frequency of potential accidents is rapidly approaching the limits of our operational response time. In the late 1970s, NASA scientist Donald Kessler began analyzing the mathematics of collision probabilities within the burgeoning field of aerospace defense. Kessler's 1978 paper modeled a specific tipping point, the moment when the spatial density of satellites exceeds the Earth's natural ability to remove them through atmospheric drag. To understand the resulting risk, we have to look past physical spacecraft and analyze the orbital environment as a statistical probability matrix. When a satellite shatters, it replaces one small target with thousands of fragments, vastly increasing the cross-sectional area available for future impacts. As this expanding cloud intersects neighboring orbital paths, it creates a feedback loop that captures more objects into the fragmentation zone. The destruction of one asset multiplies the failure probability for every satellite sharing that orbital plane. Risk models quantify this outcome using a variable called p-expect, the probability that the debris population will begin to grow exponentially. This source sink framework maps debris over 2 centuries. The top panel illustrates a sharp vertical spike in orbital fragments. In the lower panel, the green dashed line labeled t-expect marks the exact moment the growth rate peaks, identifying the formal onset of an exponential runaway. This marks an unstable equilibrium in orbital dynamics, a point where the system is primed for a total environmental collapse. At this threshold, existing fragments generate more new debris through mutual collisions than the input provided by all satellite launches combined. The risk model indicates that once this critical density threshold is reached, the orbital collision cascade becomes fully self-sustaining. In this state, the environment continues to degrade regardless of human activity. The system has reached a point of mathematical autodestruction. Cinematic depictions of the Kessler Syndrome often focus on a single apocalyptic day of explosions. The real process is far more gradual. We are more likely to encounter an economic Kessler Syndrome, where orbital slots become mathematically unusable long before they are physically blocked by debris. The primary barrier to space will be financial, the rising costs of insurance premiums, and the constant fuel consumption required for collision avoidance maneuvers. If the stochastic model is projected over several generations, it reveals the absolute physical conclusion of this sustained cascade. As fragments collide and lose energy, they will gradually lose their inclination, flattening out into a single, dense plane. This flattening process would eventually encircle the Earth in a distinct, visible ring of high-velocity shrapnel. The consequence of this shift is a multi-generational lockout, where the orbital environment becomes a permanent barrier to the cosmos. Regulatory policy and human compliance remain the final variables capable of influencing the stochastic risk equation. This chart compares d-orbit rules. The steep curves on the left show that legacy 25-year guidelines fail to stop early exponential growth. However, the blue line, a 5-year d-orbit rule, is the only tested variable that significantly flattens the risk parameter and delays the cascade. These heat maps demonstrate the danger of non-compliance. By 2082, the majority of the orbital shell is shown in critical red, representing a near-total probability of entering an exponential runaway. We are in a race to align our international policies with the compounding, relentless mathematics of our own orbital expansion. As of May 2026, a new metric tracks the safety of low Earth orbit. It is called the crash clock. Right now, without manual intervention, the time until a catastrophic orbital collision is exactly 2.5 days. Low Earth orbit has now become a densely packed web of intersecting trajectories, moving at extraordinary, uncontrollable speeds. Radar systems currently track over 27,000 pieces of shrapnel larger than a softball drifting across these flight paths. Below that threshold, millions of microfragments are moving completely undetected, acting as invisible bullets in the dark. Orbit is a finite resource. This volume of traffic is pushing the environment to the absolute limit of its capacity. In the early decades of the space age, launch rates were low. Isolated rockets carried highly specialized payloads, leaving plenty of room in the sky. The modern era of commercial spaceflight is defined by rapid, continuous deployment. Companies now launch mega-constellations containing thousands of individual satellites in tightly packed formations. This sheer volume brings us to a specific physical threshold known as critical spatial density. Critical spatial density is the exact mathematical point where we create new orbital debris faster than atmospheric drag can naturally pull it down to burn up. Once that boundary is crossed, the mass of objects in orbit creates a hard physical limit that could block human access to space entirely. In 1978, NASA astrophysicist Donald Kessler realized that the growing satellite population would eventually trigger a self-sustaining cycle of collisions. Coplanar objects in low Earth orbit cross paths at relative speeds of up to 15 kilometers per second. At these velocities, kinetic energy vastly outscales the tensile strength of aerospace aluminum and titanium. Upon impact, structures do not break, they vaporize and shatter instantly. A single collision between two intact satellites immediately produces over 10,000 highly destructive, trackable pieces of shrapnel. This initiates the Kessler Syndrome. It is a self-sustaining positive feedback loop. The math is exponential. The shrapnel from one collision strikes two other satellites. Those two disintegrate and destroy four more. The debris field multiplies uncontrollably with every impact. A localized accident very quickly becomes a permanent, expanding barrier of high-speed metal enveloping the entire planet. This instability is concentrated in specific geographic danger zones. The most volatile regions exist between 800 and 1,400 kilometers in altitude. This chart shows the spatial density of orbital debris by altitude. You can see an extreme peak exactly at the 800-kilometer mark. That massive spike correlates directly to the 2007 anti-satellite test and the 2009 Iridium-Kosmos collision, events still choking this altitude. Space scientist Vishnu Reddy notes that based on current launch rates, this catastrophic cascade is a mathematical certainty. Depending on the model, the timeline puts full saturation between 5 and 20 years from now. The window to theorize about mitigation has closed. The countdown to a self-sustaining orbital storm is active. By 2026, the strategy shifted. Aerospace agencies stopped merely tracking the dead mass and started building machines to hunt it. The 2026 Orbital Remediation and Debris Cleanup Initiative represents a coordinated move toward deploying physical, scalable hardware to clear the most congested flight paths. The European Space Agency's ClearSpace 1 mission targets a 112-kilogram payload. It approaches the uncooperative, tumbling target and wraps it securely within 4 robotic tentacles. Commercial firms are taking parallel approaches. Call Morris Inc. is developing the LAYLAP spacecraft, which relies on a multi-armed articulated system called REACT. This is the REACT system undergoing physical trials aboard the International Space Station, proving its ability to grapple solid geometry in microgravity. The inner surfaces of these tentacles use a specialized gecko adhesion material, allowing them to firmly stick to smooth satellite panels and detach seamlessly upon command. We now have the validated mechanical capability to physically retrieve massive, uncooperative dead weight from the upper atmosphere. The final barrier is economic. Launching a traditional chemical propulsion vehicle to deorbit a single dead satellite costs upwards of $100 million. In 2026, a new approach emerged: electromagnetic active debris removal, or EMAD-ADR. By utilizing electrostatic and magnetic forces, orbital tugboats move targets without physical propellant. This drops the cost of a removal mission by 95%, bringing it down to roughly $1 million per object. Statistical modeling reveals a highly achievable target. Removing just 5 to 10 large pieces of debris per year is mathematically enough to stabilize the population and prevent the cascade. Once secured by these systems, the captured debris is towed downward, allowing atmospheric friction to safely incinerate both the tug and the target. The practice of treating low Earth orbit as an infinite dumping ground is coming to an end. We are now developing the infrastructure needed to reclaim our borders and secure a safe path to the stars.